So these bitwise operations or operators are what exactly? Generally, these perform a bit by bit operation on two operands. So they will be taking each bit in one operand and performs the operation with the corresponding bit in the other operand and produces us the output. Like you can see here, 4-bit binary 1010. The negation of it is what? 0, 1, 0, 1, like that. And x and y. So correspondingly, you have to do bitwise operation. I am having here bitwise and this is. If double and is present, it is a logical and operation. If single and is present, single operator is present, it is a bitwise operator. So x and y. So 0 1 0 1 0 0 0 1 0 1 1 1. So 4-bit binary 1 0 0 0. So this is x bitwise or y, x exclusive bitwise or y, x bitwise exclusive nor y, x bitwise ampersand or and z. So this is what I can able to get the outputs, and the difference is logical operator is we are using double or symbol, and bitwise operator we are going to use single or symbol. That's it. It makes a difference. So one more thing is you need to careful. The logical operator evaluates either a logic 1 or a logic 0. But a bitwise operator is completely depending on the number of bits in your operand. So be cautious whenever a difference have to be noticed here. So the next one is the reduction operator. So what are the reduction operators in our Verilog HDL data flow abstraction? So we are having, these are my reduction operators and negation and or XOR, negation XOR, XOR, XNOR, like that. These two are same. XNOR, of course you can write here also, here also. So let me take this as an example. So what is the specialty of reduction operator is it operates only on a single operand and it produces only a 1-bit value as an output. Okay, so a equal to 4-bit binary 4 ones, b equal to 4-bit binary 0 1 0 1, c equal to 4-bit binary 0 0 1 1. Okay, if I want to perform bitwise and a, bitwise and to a and bitwise or to b, that means 1 1 1 1, all these bits are ANDed with themselves, like 1 and 1 and 1 and 1, it results me 1. And similarly bitwise operator, reduction operator I'm talking about. So reduction of b or a reduction of b, this is and the reduction b a, this is and reduction a, this is or reduction b. So what is happening, all the bits present in the operand b are ORed themselves, like 1 or 0 or 1 or 0 or 1. The sum is, it is going to evaluate to 1. That is bit. We are performing here internally bitwise OR among all the operands of your vector b and among all the operands of your vector a. Among all the bits present in your operand a, and this is among all the bits present in your vector or operand b. You are performing bitwise operation among the bits itself. That is nothing but a reduction operator. So the next one is the shift operations. The shift operation is the most notorious operator whenever you are performing it is multiplications, or it is highly employed in arithmetic and logical operations. So the regular shift operators shift a vector operand to the right side or the left side by specific number of bits as mentioned, like 4-bit binary 1011. So it is a right shift 2 times. So first shift if I have done means 0 1 0 1, second shift I have done means 0 0 1 0. That means the vacant bits are filled here. The vacant bit positions are filled with zeros. That is the thing. So here we know that this A, it is a register or it is an operand, and it is a vector, and the number of bits to shift is decided by here. Like A is greater than 2. So this is normally we call it as a right shift, and this is my left shift. Here I have written wrongly, so it is we call this one as right shift and we call this one as a left shift, like that. And this is arithmetic left shift and the arithmetic right shift. You people might be knowing that how to perform these shifting operations. And what is this conditional operator? So conditional operator also you might have encountered in some other programming language. So what is this conditional operator and what does it do is, like we do have in this conditional operator we do have here 3 operands basically. The condition expression is first evaluated. So if the result is true, then the true expression is or the true statement is evaluated as an output. If the result is false, then the false expression or the statement is evaluated as an output, like you can see. So here I am having the condition expression, select SCL. So it may be a 1 or it may be a 0 because we do have the 2 choices. If it is selection line, if it is 0, if y equal to a, if selection is 1, y equal to a, if the selection is 1, if y equal to b, if the selection is 0. So this will be evaluated as an output if it is selection is 0, and this will be evaluated as an output if the selection is 1. So it is a selection or conditional operator it is. So concatenation we discussed earlier also. Let us recap once again. I am having here the concatenation operation or the operator generally provides it's a mechanism just to append multiple operands. The operands should be definitely a sized. Why? Because unsized operands the concatenation cannot be performed. So as you can see here, all these things are of sized quantities or operands. A equal to 1 bit binary 1, 2 bit binary 0 0, c equal to, let's take an example, y equal to b comma c. I am appending b and c. So if I append 2 bits here, 2 bits here, 4 bits is the result, 4 bit binary 0 0 1 0. If I append y equal to a b, b of 0, c of 1, that means I am selecting in b, I am selecting the LSB 0, and in this c I am selecting 0 1, 1 to bit, and here I am selecting 0 8 bit. So it is a vector part select, b of 0, here also c of 1. So that means here I am extracting 1 bit, here also I am getting 1 bit, so this is also I am having 1 bit. The result is 3 bit binary 101, that's it. So this is just a simple concatenation operation, clubbing, appending I can say. So the next one is a replication operator. That is nothing but it is a repetitive concatenation of the same number by using a replicative or the replication constant. Like how many times to replicate the number inside the brackets. Like here we can see I am having a register here. This is 1 bit binary 1, register b and c, which is of 2 bit quantity, 2 bit binary 0 0, 2 bit binary 1 0. Let me take this as an example, y equal to flower brackets 4, again flower bracket here. That means 4 times I am copying, I am replicating, I am repeating 4 times what a. So I am getting here y equal to 4 bit binary 1 1 1 1 as an output here. And similarly y equal to 4 times of a and 2 times of b. B is anyhow it is a 2 bit quantity. and A is a 1 bit quantity. 4 into 1 4 plus 2 into 2 4. That means I am getting the result y equal to 8 bit quantity, that is 8 bit binary 1111. Why? Because 4 times 8 is replicated and 2 bit 2 times of b, so 8 bit binary 111100, again 00, because 2 here I am having. In the similar manner you can able to evaluate what will be the replication result for y here in the third one. So as discussed, among all the operators there should be some priority hierarchy should be maintained, like unary will be having the highest priority and conditional is having the least priority. You can observe this chart. This chart is completely depicting you the information which is the highest precedence and which is the lowest priority. Okay, so let us see some designs, some module developments by using the data flow abstractions. I am having here a 4x1 multiplexer and a carry look header logic. I will describe you how to design this 4x1 multiplexer using data flow abstraction, and this is treated as your homework. Okay. So 4x1 mux is having inputs I0, I1, I2, I3, selection line is S1, S0, output is out variable. So module mux 4x1 out I0, I1, I2, I3, S1, S0. This is not a ANSI style of declaring. It is normal sensitivity list or the argument or the port list declaration I have done normally. So again, exclusively defining what are the output variables and input variables or ports. So output OUT, input I0, I1, I2, I3, S1, S0. So in the data flow abstraction, what happens? It's only a single instruction. So within the single instruction, I have completed my execution. Like you can see here. That's it. This is the one. So within the single instruction, I have completed my program. So this is a normal data flow abstraction, like negation S1 and negation S0 and negation and I0. This is giving me Y0, Y1, Y2 and Y3. These 4 operands are ORed, and I'm getting here the result as is assigned. This expression is assigned to the output variable net of type net. Out is my variable out. Like concatenation, like conditional operation also helps in modeling my multiplexers, like assign out S1 question mark. Okay, if S1 is question mark, that means if S1 is 1, this expression is evaluated as an output. If S1 is false, this expression is evaluated as an output. Okay, let me see here once again, come back. So in this picture you can find S1 and S0. So if S, okay, I need to write here, no issue. Let me change here. S0. Yes, according to the diagram, I'm just redefining here variables. Yes, right. So if so, let me first let me get this clarity on it. If S0 is true, for suppose, this expression will be evaluated first. If S0 is false, this expression is evaluated next. Okay, if S0 is true, that means according to this diagram, if S0 is true, so S0 is true means generally what happens if it is 0 and if it is 1. So this quantity is assigned or it is passed as an output, like this entire 1 will be propagated as an output. If S0 is false, that is 0, this block will be propagated as an output. Okay, it is one. Okay, now again we have to concentrate on the internal thing. So that means I0 I1 cannot act as an output, I2 I3 cannot act as an output, only single variable should act as an output. Single variable have to be propagated here. So I0 or I1, which one will be the output of the multiplexer, will be decided by S1, and I2 or I3, which one will be the output of your multiplexer, will be decided again by S1. So S1 is the first selection line. So let me have a combination like let me go with some comments. Let me write for 0 0 selection line, I0 is to be evaluated. For 0 1 selection line, I1 is the output. For 0 1 0 selection line, I2 is the output. For 1 1 selection line, I3 is the output. Okay, so what's happening? I0 0 is, that means it is S1 S0. So S1 and S0. So S0 S1, this is because S0 S1 according to diagram I am following. So whenever 0 0 means I0. So S0 is 0, the MSB is 0, and okay, according to diagram I am having like this. This is 1. Okay, so S1 should be 1 1 0 1 1. S0 S1 0 0. Okay, and 0 1. Okay, 1 0. Okay, 1 1. Right. Yeah, we are right only here. So first in this one, S1 S0, instead of S1 S0 I have taken as S0 S1 as the selection line. S0 S1. So when S0 S1 are 0 0, I0 is evaluated. You can see the diagram. S0 S1 are 0 0. So S0 S1 are 0 0 means S0 have to be concentrated first. S0 0 means this multiplexer is evaluated as an input. For the output of this multiplexer is evaluated as an input as first input for this multiplexer. So 0 0. Okay, so 0. Next is S1 is also 0, that means 0. So I0 is evaluated as an output of this multiplexer, so output will become I0. So next is 0 1. So anyhow it is S0 is 0, and now S1 is becoming 1, that means I1 is evaluated as an output. So for 0 0 and 0 1, for 0 0 and 0 1, I0 and I1 will be evaluated as an outputs for 1 0 and 1 1. So now selection line S0 is 1 and the selection line S1 is 0 1 0. I2 will be the output. For 1 1, I3 will be the output. So this is how happening. Let us see back here also. So if S0 is true, and that means 1, like I'm discussing about this thing, this combination. If S0 is 1, S1 is 1, S0 is 1, that means two conditions have to be evaluated, and S1 is also 1, S1 is also 1 means among these two true conditions have to be evaluated. That means I3 is emerging as an output. So I1 for S0 S1 selection line as 1 1, I3 will be the output. Similarly for 1 0, so S0 is anyhow 1. Now S1 is 0, so S1 is 0 means I2 false condition will be evaluated. That means first this expression have to be evaluated first. Why? Because 1 0 S1 S1 S0 S1, here I have seen 1 0 S0 S1 1 0. So this true condition have to be evaluated first, and next inside it I need to check what is the other selection line, that is s1 is 0 here, so definitely I2 will be evaluated as an output. Similarly for s0, for a 0 for this condition, this expression is evaluated and as an output, and again I am having s1 as 1, so I1 will be evaluated as an output. Next is s0 0, s1 is 0, so s0 0 means this false expression evaluated as an output, and s1 is 0 means the false variable, that is I0 is evaluated as an output. So in this way the conditional operator is highly benefitable whenever we are modeling any hardware design by using data flow abstractions. Let me exhibit one more data flow design, that is 1-bit full adder. So okay, I said yeah, you can take this as a homework, carry look ahead adder logic. So you can design this carry look ahead adder logic if you know what are the internal blocks and how the data is flowing between one block to other block. If you know, you can able to design in data flow modeling to develop this hardware. Okay, thank you for today.